Hello and welcome to the video for the optional material in Chapter 2. The optional material in Chapter 2 is going to cover the following topics, and just as a heads up, this is probably going to be the most difficult of all of the optional material in all of the chapters. Is the Chapter 2 optional material. That's why I'm doing a video for this one first. So the first topic is going to be the biconditional truth function. We did the biconditional statement operator in Chapter 1 optional material, but now we'll look at the truth function. We'll discuss the topic of functional completeness and disjunctive normal form, the Sheffer stroke, which is another statement operator, and the NAND function, which is the truth function that it stands for. And then I'll show you some example problems of the sort you can expect to see on Quiz 2 and also the final exam. So the first topic is the biconditional truth function. And in the Chapter 1 optional material, we discussed the biconditional operator. And it was translated natural language expressions that would be like if and only if B, A if and only if B, A is necessary and sufficient for B. And the symbol that we used for that was this, wow, my arrow is really bad, was this triple bar. So that's our symbol for the biconditional operator. The truth function is this. And you can see that, here's one way to think about it. You can almost think of this as an equals sign, saying that the truth value of A and the truth value of B are the same. So in row 1, they're both true, so it's true. And in row 4, they're both false, so they're also equal, false equals false. But in rows 2 and 3, they're different, true, false, and false, true. So they're unequal. So it returns false in all of those cases. Okay, so that's the easy way to think of it, is just in terms of like equal truth values. But this is the truth function for the biconditional. Now, it was pointed out in Chapter 1 that the biconditional, it's expressed verbally in natural language in English, almost like it's the conjunction of two conditionals. So you say if A, if and only if B, is really short for A if B and A only if B. And if we translated this into notation, it would be this and that. So it's the conditional that uses A and B going in both directions. If B, then A, and if A, then B. Same thing for A is necessary and sufficient for B. A is necessary for B would be that. Remember how to do this. And A is sufficient for B. So either way you look at this, it's really a conjunction of the two conditionals. And you can, if you do a truth table, so here in column 3 is the truth function I just gave you for the biconditional. If we actually do the truth table for the conjunction of the two conditionals here, you can see it's the same, true, false, false, true. So not only does the natural language reflect the idea that it's a conjunction of those two conditionals, the truth function also reflects that fact. Okay. Now, this leads to the next topic. And when I say this leads to the next topic, what I mean to say is the fact that this is the same function as that. So remember that. The next function, or the next topic, is functional completeness. What does that mean? Well, how many truth functions are there? Let's just start with that question. So in the normal material, we talk about 4 operators and the corresponding functions: negation, conjunction, disjunction, conditional. In the optional material, we added biconditional. And you might wonder, are there more truth functions or operators besides just these? And here's one way to think about this. So what's the difference, let's say, between this function and any of the other functions? But let's just say this one. Well, they're the same on all of the rows except here. This one has T when this one has F. Well, this leads to the following thought. We could just make up a new truth function if we just, what would be a truth function we don't already have? False, 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 true. And if you look, this isn't like any of these, okay? It's very similar to this one. It's just different in row 1, but rows 2, 3, and 4 are the same. So this is potentially another truth function that we haven't already talked about. Well, once you realize that what makes truth functions different is just the different patterns of outputs that you get for the same inputs. This means that there's actually, we know exactly how many functions there are. There's 16 because there's 16 possible output patterns for a two-place input pattern. So all I've done here is this is just a regular truth table. I've got my two components here. And what I've done is I've just filled out all of the possible functions, kind of like how we fill out truth tables normally. In the top row, I did the first 8 true and this last 8 false. Then I alternated by groups half of big. I did 4 trues, 4 false, 4 trues, 4 false. Then I alternated by groups of 2 and alternated by groups of 1. And that was just the method I did. But you can see that gives us 16 possible functions. And a lot of our functions are already on here. So if you look at F8, that's conjunction. It's true when both inputs are true, false otherwise. F7 is the biconditional that we already talked about. F5 is conditional, if alpha then beta. Okay. But you can see that the functions that we've already talked about are just a handful of the possible truth functions that are up here. Now the next question is, so if there's 16 two-place truth functions, how many operators do we need? Okay, and here's what I mean by that. So here's 16 truth functions. Remember what I said about the fact that biconditional is the same thing as a conjunction of two conditionals. Well, what that means is that we don't need an operator for biconditional as long as we have an operator for F5 and F8. F5 is conditional, F8 is conjunction, because anytime we have this truth function, F7, we can just replace that statement with a conjunction using this of two conditionals using that. So even though we need this function, right, this is one of the 16 possible functions, we don't need a separate operator for this function because we can capture this function using an operator for this and an operator for that. Okay. Moreover, we don't need an operator for F10. What's F10? F10, actually, how about what's a good one? Let's look at inclusive or exclusive or. Actually, that's F10. So exclusive or. Remember, all of our disjunctions that we use in class are inclusive, and that would be here, F2 is inclusive disjunction. This is another truth function, exclusive disjunction. Well, we don't have an operator for that, at least not in the way I'm doing the class, and we don't need one because we can re-express this operator using inclusive or conjunction and negation. Okay, in particular, if we use this as an operator for exclusive or, alpha XOR beta will be equivalent to alpha inclusive or beta and not alpha and beta. Okay, so I don't need this operator as long as I have disjunction, conjunction, which I use twice, and negation. Okay, so then the question is, we've seen that there's a couple operators we don't need. We can express all 16 functions with a smaller set of operators. We don't need one for F7 and we don't need one for F10. So you might wonder, what's the smallest set? Can we get rid of more of these operators? And the answer to that leads us to the next topic, which is disjunctive normal form. By the way, this word functional completeness, what this means is that a set of operators is functionally complete if you can express all truth functions with just those operators. And so we ended this section by just asking a question. What is the smallest, or are there, how many of these can we get rid of and still be functionally complete? Well, one answer to this is disjunctive normal form. So one functionally complete set of operators is disjunction, conjunction, and negation. And so here's how you can sort of get your head around that. Let's look at the conditional truth function. When does this function return the value true? Well, as you can see, there's three cases, right? It's true when A is true and B is true, row 1. It's true when A is false and B is true, that's row 3. And it's also true when A is false and B is false. So these are the situations where conditional outputs true. Well, look, we can re-express this as A is true and B is true, or A is false and B is true, or A is false and B is false. These are the conditions where conditional outputs true. And just A and B, so I'm turning false into negation and just getting rid of true. So we can re-express this as A and B, or not A and B, or not A and not B, which is then just this. So the conditional function really can be re-expressed as this: A and B, or not A and B, or not A and not B. And in fact, if we do a truth table for this, so here I've got the conditional on column 3, and here I have this statement here at the end. Notice I have 3 disjuncts and 2 disjunction operators, but I haven't grouped them in the optional material. That's fine to do that with disjunctions and with conjunctions. We don't need to, we can just fudge that. But you'll see this is in fact exactly the same function: true, false, true, true. Which it kind of has to be, because these are just literally these 3 rows. These 3 disjuncts are just literally the representation of these 3 rows. And it's this one that makes this true. This one puts a T there, and this one puts a T there. Okay? So this leads to what we'll call disjunctive normal form. In fact, this statement here is a statement in disjunctive normal form, and I'll give you the definition of that in a minute. But first we need a definition. One definition, what we're going to call a literal, is either an atomic statement or the negation of an atomic statement. We're just going to call that a literal. And with that definition in hand, this is where the negations come from. Disjunctive normal form will be a disjunction of conjunctions of literals. And remember, literals can involve negations, and so that's why we need the negation operator as well. And this was the statement we had, and we can see it's a disjunction. So the whole thing is basically 3 disjuncts. So this is a disjunction with 3 disjuncts. Each disjunct is a conjunction. So that is a conjunction, that's a conjunction, that's a conjunction. And for each conjunction, the conjuncts are literals. Atomic statements, negated atomic statement, negated atomic statement, negated atomic statement. So this is disjunctive normal form. Okay, a disjunction of conjunctions of literals. And you'll notice that it's possible to read the disjunctive normal form of any function directly off the truth table. That's exactly what I did for conditional. Okay. So for instance, suppose you wanted to find the disjunctive normal form for F11 here. Well, you just look at where it's true. It's true on row 2. It's true on row 4. So row 2 is A is true, B is false. Row 4 is A is false, B is false. So it would be A is A and not B. That's row 2. Or not A, and not B. That's row 4. So this would be the disjunctive normal form of F11. And you just read that directly off the truth table, or that's one way you can do it. And this will be a disjunction of conjunctions of literals. Now you might wonder, what about F16? Okay, because the recipe I just gave you will work for all of them, F1 through F15, except what do you do here when none of the rows are true? It's a little bit of a fudge because in one sense, you know, technically we could allow a disjunction with only one disjunct, okay? But here it would be a disjunction with 0 disjuncts, which might technically be correct, except that then you couldn't tell the difference between someone who answered the question correctly and someone who just skipped past the question. Their paper would look the same. So we want to have just something to say about what to do with F16. Well, you'll notice F16 is just false, returns false everywhere. So this is, no matter what the inputs are, it returns false. So it's essentially just a contradiction. So A and not B. That's in disjunctive normal form. It's one disjunct. That disjunct is a conjunction of literals. If you really wanted to, if you don't like the idea of a disjunction with one disjunct, we could just repeat that disjunct A. I'm sorry, this should be A and not A. I don't know why I put that A and not A. That's a contradiction. So that would be a disjunction with one disjunct. And if you really don't like having only one disjunct, we could just repeat it, A and not A. So this is a disjunction of conjunction of literals, and if we did a truth table for this, obviously it would be falses all the way down, so it would capture F16. Okay. So we can just use that to capture F16. Now, the next topic is what we'll call canonical disjunctive normal form. So disjunctive normal form, remember, is a disjunction of conjunctions of literals. But the problem with that, and this may or may not be a problem, but in some cases, situations, this might be a problem. For any given function, there might be a lot of different disjunctive normal form representations of it. So for instance, this is the one we just gave for conditional, but this is also a disjunctive normal form for conditional. And I got this just by swapping, changing the order of some of these. I put this one there. I put this one at the end, right? So I just changed the order of disjuncts, but it's a different statement. It's a different representation. This is also that what I did here is I just kept this one, but then I added this disjunct at the end, which doesn't matter because, I mean, it's a contradiction, but these are disjunction. It's a disjunct, so it's still equivalent to just this. But you can see it's still a different statement. And so for any truth function, if I just gave that function to two people and said, hey, re-express this in disjunctive normal form, they might come back with two different statements, but still both be correct. Okay? And in many contexts, that's not a problem. In some contexts, it is. If you're grading papers for a logic course, it might be convenient if everyone would produce the same disjunctive normal form representation. It also, if you're doing a circuit design where you're actually computing logical functions by designing circuits where a voltage in a circuit is equivalent, it is essentially true or 1, and no voltage is, say, a 0 or false, and you want a circuit that will compute different functions, and you want to break those functions in disjunctive normal form, it might be convenient if you could always break any given thing down and you could be confident that it would be the same statement. So one way to do that is what's called canonical disjunctive normal form. So a definition of or a way to get at canonical disjunctive normal form would be this. Again, literals are the atomic statements and the negations of the atomic statements. So far, so good. The conjuncts of the conjunctions are the inputs that make the function true, and you get these right from the truth table, the way we've been doing it. The disjuncts of the disjunction are these conjuncts in order from top to bottom on the truth table. Okay, So for example, the function I did here is canonical disjunctive normal form as we've just defined it, because I've read it directly off the truth table. This is row 1, this is row 3, this is row 4. So I went from top to bottom. The literals are in alphabetical order, and I just read them straight off. And so if I gave the conditional truth function to two people and said, give me the canonical, the CDNF form of this, they should come up with exactly this if they're doing the truth table the right way by having atomic statements in alphabetical order, and they're reading these disjuncts from top to bottom from the truth table. Okay. Next function, or next topic. The Sheffer Stroke, which is another statement operator, and NAND, which is another function that we'll talk about. It's function, I think it's F9 on the table that we had. Well, so far, I mean, we asked a question, which was, do we need all of the operators? And we answer that by saying, well, we can get rid of some of the operators, right? We don't need biconditional because we can re-express that with conditional and conjunction. Disjunctive normal forms shows that you can actually trim it all the way down to 3 and re-express all 16. You might wonder, is there even a smaller set? Maybe you could do with 2 or 1. The first thing to notice is that not any set of operators is going to be functionally complete. You might think, oh, it's just a matter of how clever you are. If you could do it with any operators. You just might have to be clever in terms of how you reconstruct all 16 functions using only 2 or 3 or 4 operators. And that's not true, because not any set of operators is going to be functionally complete. So for instance, conjunction and disjunction aren't. So disjunctive normal form uses conjunction, disjunction, and negation. You might think, well, let's just get rid of negation. Let's just use conjunction, disjunction. That's not going to work. And here's one way to see it. So here's conjunction and disjunction. And suppose you wanted to re-express F12 here. You should be able to see there's no way you're going to be able to do that. And one way to see that is notice that conjunction and disjunction have a certain feature. When both inputs are true, they output true, which means that you can combine, you can embed and sort of, recursively embed conjunction and disjunction with each other all you want. Row 1 is always going to come out true, because the components of, no matter how complicated that function is, the components, if they're only conjunctions and disjunctions, are all going to be true on that top row, because these atomic statements are true on the top row. So you'll never be able to recapture F12, for example. So this is just one way to see that, for instance, not any set of operators is going to be functionally complete. Conjunction and disjunction aren't. Conjunction and inclusive disjunction aren't. Well, there is a smaller set, though, and that is the NAND function, which is here in F9. And we have an operator for that, which is called the Sheffer stroke, and that's just this line here. So if we want to have a written operator for this function, it'll be like A stroke B. Okay. Well, the NAND function is actually, it's called NAND because it's the negation of AND. Okay, and if you actually look here, F8 is conjunction, or AND, true, false, false, false. F9 is just the negation of that. Okay, it's false, true, true, true. So F9 is just the negation of the conjunction, or negation of AND, NAND. It turns out that that one function, this one operator, Sheffer stroke, which stands for F9, is functionally complete. We can re-express all 16 truth functions using just that one operator. Now, how do we know this? Okay, how do we know that this one function, this one operator, is functionally complete? Well, how did we know that disjunctive normal form was functionally complete? Let's start with that question. Well, we knew it was functionally complete because I introduced it in a way that made it clear how we could re-express all 16 functions. And the only one that was a little bit iffy which was that F16, the one on the end, it was all false. I showed you how to do that one too, in a way that still only used those 3 operators. So one way you could show that any set of operators is functionally complete is just to actually re-express all 16 functions, show how you can do it with just those operators. So you might, think, okay, well, one way to do it is just to, for each function, express it in with a Sheffer stroke, which you can do. So that's one way you can do it. But there's another way, actually, to think of it, which is this. We already know that the set of operators, disjunction, conjunction, negation, is functionally complete. That's just disjunctive normal form. Well, that means that if we can express those 3 in terms of the Sheffer stroke, then we know the Sheffer stroke will be functionally complete. Okay? Because if those 3 are functionally complete, if we can re-express them, we can re-express anything. So I'm going to show you how to express any 2-place, the functions negation, conjunction, and disjunction using the Sheffer stroke. Remember, Sheffer stroke for alpha stroke beta is just a negated conjunction. It's just the negation of A and B. Okay, which means that one way to think of this, remember, if you're just doing the truth table for A and B, the way to do it is you look for where these are both true, and it'll be true there and false everywhere else. This is just a negation. You look for where these are both true. It'll be false there and true everywhere else. Okay? Well, how can we re-express not A using only the Sheffer stroke? Well, here's how. Notice that not A is going to be equivalent to the conjunction of not A and not A, right? So basically, we just need to express that. And the way to do that is, well, actually, I don't know if that was terribly helpful. Here's the way to think of it. This is the truth function for not A. It's false when A is true, true when it's false. Now let's look at this, A stroke A. This is going to be true when they're both false. Well, where are the inputs of both false? Well, they're both false on 3 and 4, so it's true there and false everywhere else. And you can see it's equivalent. A stroke A is the same as not A. So anytime we have not statement, and we want to get rid of that negation, we want to re-express this without the negation, we do it just by taking that statement itself and putting it on both sides of the Sheffer stroke. So that's how we can express any negation. Anytime we have a negated statement, we just replace it with the statement on both sides of a Sheffer stroke. We can do the same thing with not B. So B stroke B will just be false, true, and again, you can look at this, look for the rows where both sides are true. Well, they're both true on rows 1 and 3. So it'll be false there and true everywhere else. What about conjunction? Well, this one is, if you think about it, it's pretty easy. Okay, and why is that? Well, remember, the Sheffer stroke is for any 2 statements, let's just say A and B, A Sheffer stroke B, is the negation of the conjunction A and B. Okay. Well, what that means, if you think about it, that means that, let's just negate both sides. If we negate both sides of this, that means not A stroke B is equivalent to the negation of the negation. So we negated this, let's negate that, of A and B. And both of these negations cancel out. So not A stroke B is equivalent to A and B. So if we want to re-express conjunction, we can do it as the negation of A stroke B. Okay, but what about this negation operator? Well, we already know how to re-express negation. We negate something, by just putting that statement on both sides of a stroke. So how do we negate this? A stroke B. That's a B, by the way. Stroke A stroke B. That's not written very clearly, so I'll do it again. A stroke B, stroke A stroke B. So we just negated that, and this is the negated conjunction. So that's how we get a conjunction, is just by this. A stroke B, stroke A stroke B. It's the negation, okay, of what? This is negation because it's the same statement on both sides of a stroke. Negation of what? Negation of NAND. Well, NAND is the negation of a conjunction. So if you negate the negation of a conjunction, that's just the conjunction right there. So that's the way to think of that. How do we do disjunction? Well, here's the way to think of disjunction. Notice that, I'll do this up here, A or B. Let's do De Morgan's on this. So equivalent to not the negation of not A and not B, right? So how would we put this in terms of Sheffer stroke? Well, again, we want to get rid of these things. So the A, not A, would just be A stroke A and B stroke B, and that whole thing is negated, right? So here I'm just re-expressing this as this. I change the negations into negation A into A stroke A, negation B into B stroke B. Well, this is just a negated conjunction, which is exactly what the NAND operator represents. So it'll just be A stroke A stroke B stroke B. Okay, and so I'll just write that here. So this is how you would express inclusive disjunction using the Sheffer stroke. If you just memorize these, and you can reconstruct this table if you need to, but if you just memorize these, you express negation this way, you express conjunction this way, you express inclusive disjunction this way, you'll always be able to turn any statement into the Sheffer stroke, any statement in DNF into a Sheffer stroke representation. Well, given that, let's look at some example problems, the kinds of problems you might get for Chapter 2 optional material. So you'll get questions, for instance, on the biconditional truth function, functional completeness, disjunctive normal form, or well, all of those. But in particular, what you want to do is know and use the biconditional truth function, not just the operator. So in Chapter 1, you learned the operator. How do you translate from English into formal notation using the operator? Now you'll want to be able to use that in truth tables and such. Understand disjunctive normal form and canonical disjunctive normal form. Understand the NAND function and the Sheffer stroke operator, and in particular be able to re-express any function in terms of either canonical disjunctive normal form or the Sheffer stroke. So here's an example of using the biconditional truth function, also using the Sheffer stroke. So use a truth table answering the following questions. This is exactly the kind of thing you would do in the normal material, except if you'll notice here, these statements involve a biconditional. They also involve a Sheffer stroke. So you should just be able to do truth tables using these operators and answer questions about them. And so in this case, if we do the truth table for these three statements, not R stroke S, not S if and only if R then not R, and S and R. So I've just done a truth table that has these right here. And we can double check that this is correct. So RS, R NAND S, this will be false where they're both true, true everywhere else. That's right. Not R is the negation of R, not S is the negation of S. If R, then not R. So if true, then false is false, true, false, false. Negation of R stroke S. Well, of course, this is also going to be the same as the conjunction, right? It's the negation of NAND. So NN AND would just be AND. So they're both true here. False, false, false. This is the second statement. I won't walk you through it, but you can see that well, I guess I will walk you through it. They're equivalent here and they're equivalent there. So it's true on 1 and 4. They're different on 2 and 3. So it's false there. And this is just S and R. True, false, false, false. So that's the truth table. R1 through 3 equivalent. Rows 1, 2, and 3 they are, but if you look on row 4, there's a difference. So no. They're not equivalent. Are they consistent? Yeah, it's possible for them to all be true. Right there. So yes. And you'd explain, are they equivalent? No, they differ on truth value on row 4. Are they consistent? Yes, they're all true on row 1. Do 1 and 2 jointly imply 3? Let's see. So we're going to look for a counterexample row where 1 and 2 are true, but 3 is false. And there's no counterexample row, so yes. Do 2 and 3 imply 1? Is there a counterexample row where 2 and 3 are both true, but 1 is false? No. So that implication also holds. So this would be an example of using the Sheffer stroke and biconditional operator in truth tables to answer questions. So make sure you can do that sort of thing. Next off, for understanding disjunctive normal form and canonical disjunctive normal form, you might have questions like this. You might make sure you can re-express any function, both in terms of canonical disjunctive normal form and Sheffer stroke. So you might get a question like this. Look at F14. This was one of the functions we had. Re-express this in terms of the Sheffer stroke, and then use a truth table to demonstrate that your Sheffer stroke representation is correct. How would you do that? Well, the first step, the easiest way, is to first express it in disjunctive normal form and then translate the disjunctive normal form into Sheffer stroke. Well, what's the disjunctive normal form of this? Well, it's only true on row 3, so it will be not alpha and beta. And there's only one disjunct in this DNF. Okay, so that's I'll just rewrite this up here. Now we just need to express this in terms of the Sheffer stroke. Well, there's two parts. We need to get rid of this negation. We need to get rid of this conjunction. How do we get rid of the negation? Well, remember, to negate something, we just take that thing and put it on both sides of a Sheffer stroke. So we'll have alpha stroke alpha. That's replacing this. And beta. So we haven't gotten rid of the conjunction yet, but we've gotten rid of the negation. So, oh, by the way, I'm just reminding myself here of how to do negation and how to do conjunction. So this is what we get when we get rid of the negation. Negation A is replaced with A stroke A. How do I get rid of conjunction? Well, I just take each conjunct. I take the conjunction and instead I replace the dot with a stroke, and I put that same thing on both sides of a stroke. Okay, that's essentially how this works. So it's going to be, I'm going to replace this with a stroke, and then I'm just going to duplicate it on both sides of a stroke. So it will be alpha stroke beta, and then this whole thing on both sides of a stroke. Alpha stroke beta. Okay, and now I've gotten rid of the conjunction. And it looks like this to make it look nice. Okay, so this is kind of my answer right here. I've re-expressed F14 in terms of the Sheffer stroke. Now the next step, part of it, is to do a truth table to show that I got it right. So now I'm going to do a truth table for this function. And it will look like this when I do it. So Here's alpha and beta. We can just walk through it. Alpha, well, this will return false when both sides are true, true everywhere else. Well, both sides are true only on rows 1 and 2, so it's false there, true everywhere else. So, and again, this is just how we're negating it. Now, where are both sides of this true? Well, they're both true on, here's both sides, they're both true only on 3. So it'll be false on 3, true everywhere else. Now, where are both sides of this true? Well, both sides of this is just a duplication. Both sides are equal to column 4 here. So where are both sides true? 1, 3, and 4. So it'll be false on those and true everywhere else. Boom. So that's the right truth column for that. Here was F14, and you can see that they're the same. So that's how you would demonstrate that you got it correct. Okay, well that's it for this material, for the Chapter 2 optional material. Just make sure that for any function you can re-express it in terms of disjunctive normal form and the Sheffer stroke, and it will help you if you memorize the ways to get a disjunction, conjunction, and negation into the stroke notation. So that would be going back here just a couple of slides. Well, this is negation, that's conjunction. But if you'll recall, we did disjunction before that. Okay, and that's it. So good luck with the optional material.